Okay, question 2. A bar has a total length of 1 metre and a constant diameter of 50 mm. 3/4 of it is in steel and 1/4 is aluminium, joined by some kind of mystery method. What will be the total extension of the bar when it's subjected to an axial tensile load of 100 kilonewtons? Take Young's mod for steel to be 200 gigapascals and 70 gigapascals for aluminium. Okay, standard thing to do is draw a diagram. So let's do that. A bar has a total length of 1 metre or 1 metre. Constant diameter of 50 mm, which is 0.05 meters. This gives a radius of 0.025 and an area of pi times 0.025 squared. Now I'm taking a very tiny risk by calculating that. The chances are we're going to need the area. If it's any kind of stress calculation, stress is force over area, you can bet your bottom dollar that if they're giving you a diameter, we're going to need an area. So let's just do that for the second it takes. So pi times 0.025 squared is equal to 0.00196. And it's constant throughout, unlike question 1 where it had different diameters. Right, 3/4 of it's from steel. So let's say that this first 3/4 is steel. That's 0.75, and that's steel. And then this remaining part is aluminium, and that is 0.25 meters, where the Young's modulus of steel is 200 gigapascals, 200 times 10 to the 9. Remember, immediately interpret that as times 10 to the 9, otherwise you'll just be putting 200 into various formulae, which will screw you over. So Young's mod for aluminium, we said 70 gigapascals. It's subjected to an axial tensile load of 100 kilonewtons. So remember, axial just means along the length of the thing, along the axis. F equals 100,000 newtons. Good. What will be the total extension of the bar? So we know that Young's modulus is equal to stress over strain. That's probably going to come in useful. And we know that strain is equal to the change in length over the original length. And I think this is going to be pretty much the same as question 1, whereby you work out the extension in the first section, extension in the second section, plug them together, and then you'll get an answer. Quite strange if that's basically the same question in the first 2 bits of the paper, but we'll go with it. So then let's plug in what we've got. So let's do the steel case first. So for steel, we know that Young's modulus E is equal to 200 times 10 to the 9. That's 10 to the 9, which is equal to stress over strain and we know that the stress is equal to the force over the area, which is going to be equal to force is 100,000. Actually, I've written a comma, and avoid doing that, it's poor form, gets confused with decimal points. 100,000 over the area, which was this thing here, 0.00196, which is equal to 50.93 megapascals. And the way I think I'll lay this out is I'll have a 4 aluminium case over here. Right then, so let's go back, let's plug this value back into here. So to do that, we will have 200 times 10 to the 9 is equal to 50.93 times 10 to the 6, which of course is this value and that value, it's the same thing, all divided by our unknown quantity epsilon. So we can then write that epsilon is equal to, take this up here, that under there, that will be 50.93 times 10 to the 6. Epsilon strain, I should really start calling that strain, divided by 200 times 10 to the 9, which is equal to 0.0000255. And strain's a unitless dimension, and we know that strain is equal to delta L over L. We're interested to find out what delta L is, so we can say that delta L is equal to strain times the length. I'll just rearrange that up there. So let's plug in this number and the original length of the steel, which is there. So we're going to have the change in length is equal to 0.0000255 times 0.75, which is the original length of the thing. So the extension in the steel part is times 0.75 is 0.00019 meters. Do the same for the aluminium. Well, the stress is going to be the same, because it's just force over area. So I can write that the stress is equal to this thing, 50.93 megapascals. It's uniform cross section, so stress is just force over area, same force acting across the whole area. The only difference is there's a different material. So we'll follow the same process. So we can say that the Young's modulus of aluminium was 70 gigapascals, so 70 times 10 to the 9. We use stress over strain. We'll just repeat the process. So Young's modulus equals stress, which is this thing, 50.93 times 10 to the 6, divided by our unknown quantity strain. So therefore strain is equal to 50.93 times 10 to the 6 divided by 70 times 10 to the 9. Just rearranged effectively this formula with the numbers that we know. So that gives us a strain value of 0.000728. So using this same thing here, we'll have change in length is equal to strain times the original length, and that's going to be equal to 0.00728 times the original length of the aluminium, which is 0.25, Not that you'd know it from my diagram. 0.25, and that is equal to times 0.25 0.0000182 meters. So therefore we can say total change in length is equal to A plus B. Write it out longhand in the exam. I'm just being lazy with the graphics tab look there. So I'll just sum these two in a calculator. So I'll add to that 0.00019. That gives us a total extension in meters of 0.000372 meters. They'll probably want it in millimeters, so we'll times it by 1,000, and we're getting a total extension of 0.371 millimeters. Oops. That's my answer. Let's check it. .373. I think that's within the realms of rounding error. Right, happy days. 10 marks, 10 minutes, near enough. So just to recap, whenever you get these split part problems, whether they are split in terms of material or split in terms of size, work out the stress in each respectively, then work out the strain one way or another. So in this case we just use stress over strain, and then sum it up at the end. Make sure you realise that an axial tensile load sounds fancy, it's just the same stretching force throughout the entire structure. Lovely. Let's have a go at part B. Okay, we're really flying now. A beam is simply supported and has a 5 metre span, so L's 5. It's made from tubular cross section with an inner diameter of 0.8, the size of the outer diameter. Okay. Calculate the required beam diameters when a 1 kN load is applied mid-span and produces central deflection. So this is a key word, isn't it? Deflection. That's your Dmax formula of 2.7 millimeters. Takes a Young's modulus of 200 gigapascals. Right. I imagine you, like me, are not going to be 100% sure how you're going to tackle this, so just draw a diagram. Then state your variables, then any formula you think are going to be relevant. Let's do it. So a beam, that can be a beam, is simply supported, okay, so simply supported there, and has a 5 metre span. It is made from a tubular cross section. Let's see how accurately I can draw a circle on this thing. Not bad. And the inner diameter is 0.8 that of the outer diameter. Okay, how can we say that algebraically? So if we call this big D, then this is 0.8 D. Now that makes sense to me algebraically. It may well do to you. If not, I've seen this kind of question come up before actually, come to think of it. This is a relatively standard way of dealing with this problem. So calculate the required beam diameters. So in other words, if you work out D, you'll times that by 0.8 to work out the inside. Calculate the required beam diameters when a 1 kN load is applied mid-span. Goodness me, like a countdown conundrum, this thing. So we've got a 1000 Newton at mid-span 2.5 meters, that's what that means. And produces a central deflection of 2.7 millimeters. So that's your maximum deflection. D max, or delta max rather, is 2.7 mil. Now you can do that in your head. Exam situation, don't make a stupid mistake. So just do 2.7 divided by 1,000, just to be absolutely sure. 0.0027. Because you can get it wrong. Well, we know we're definitely going to need the formula involving D max, which you're probably sick of after your coursework. That is for a simply supported beam with a point load in the middle, FL cubed over 48 EI. Let's write that down. So D max equals FL cubed over 48 EI. We know that if they give you some geometry, chances are you're going to need I, and that's exactly what we're going to need this time. So we know that I for a tubular section is pi d to the 4 minus d to the 4. So that'll be pi big D to the 4 outside diameter minus little d to the 4 over 64, was it? 64. Right, this is where it gets not complicated but algebraic, and we need to think about it. We know that little d is effectively 0.8 of big D, so let's write that in. So we'll have pi d to the 4 minus, now these brackets are all important, 0.8 d to the 4 over 64. So if we crunch that, we'll end up with pi d to the 4 minus, so we've got to take 0.8 to the power of 4, which is a nightmare to do on a phone. Don't forget your calculator in your exam. 0.8 to the power of 4. 0.4096 d to the 4. All over 64. So we can now rewrite this as in terms of just d to the 4. You know, simply, if this was 3d to the 4 minus 1.5d to the 4, then that would be equal to 1.5d to the 4, wouldn't it? So, applying the same principle, if we have d to the 4 effects, we've got 1 minus 0.4096 d to the 4. So let's try that. 1 minus, my kingdom for my Casio calculator. Let's write in this. 1 minus 0.4096, okay, is equal to, I'll rewrite it here for ease, I equals 0.pi times 0.5904. It's horribly written, I'll just neaten that up. Pi times 0.5904 d to the 4 all over 64. Now you've got to really pay attention to that step. It'd be very easy just to go, oh, d to the 4 minus 0.8 d to the 4, that's 0.2 d to the 4, but it's not. We're replacing the little d with 0.8 d. So we actually have to raise the 0.8 to the power of 4, which is why we end up with this odd number here. If you do that, the rest of it's pretty plain sailing. So let us just remind ourselves what we're trying to do. We're trying to calculate D. Because if we have a value for D, we've got the outside diameter, and then we just times that by 0.8 to get the inside diameter, and that's what it wants us to do. Calculate the required beam diameters. So what we're going to do is we are going to rearrange this formula to find I. Then we're going to plug I into here, rearrange to find D. Okay, so let's go from this point here. Okay, I'm going to rearrange it algebraically first, so I'll have D max times 48 EI is equal to FL cubed. Just taking that up there. I'll take everything else apart from the I under here. So I'll have I is equal to FL cubed all over D max 48 EI. Plug in the numbers, so we'll get I is equal to 1000 newtons times 5 meters in length cubed, L cubed, over D max, which we calculate at the top here. Well, we didn't calculate it, was given to us, 0.0027 times 48 times E, which is Young's modulus, 200 gigapascals, times 10 to the 9. I like to put those in brackets just to avoid confusion, times I've got confused here, haven't I? It's not E at all, I'm just bringing this under, so it's I is equal to D max 48E. So that's that. Right, let's crunch that in the calculator, which is equal to 0.50, Of course, you would just hit the ENG button there, but I can't do that on my phone. You'd be writing it in standard form to avoid errors. Right, we need to plug that thing into this. So we'll have, I'm going to copy that so I don't have to write it again. That's I. I times 64, so I'm bringing that up here, divided by pi, divide both sides by pi, is equal to 0.5904 d to the 4. So we'll just crunch that in the calculator. So 0.123454822 times 64 divided by pi is going to equal 0.1234982. Bring that under, divided by 0.5, which is equal to 0.0000166, which is equal d to the 4. So if we take the 4th root of that thing, we should have a value for d. Let's do that now. Everything is so much harder without one of these Casio calculators, goodness me. Right, let's try again. 0.123166. I want to do the 4th root of that. So I reckon that D is equal to 0.1135 meters, which is equal to 113.5 millimeters. So the smaller diameter will be 0.8 of that, which I'll times that by 0.8, which is equal to 0.0908 meters, which is equal to 90.8 millimeters. Let's check that. (113.5.6), 90.8. There we go, close enough. So that was, excuse the slightly chaotic layout of that, but I can't stress what a total nightmare doing calculations like that are on a phone. Don't forget your calculator. But particularly rewatch this first section because I've seen these exam questions pop up before, and it's quite a subtle point that. It's really tempting to just go d to the 4 minus 0.8 d to the 4, 0.2 d to the 4. But no, when you crunch it, you get this weird situation here. So just be aware of that and practice it. On to question 3.